Hello, it's Keith here, and this is lesson 25 of the simple series of my Z80 assembly programming tutorials. Today we're on the ZX Spectrum again, and we're taking a second look at my sprite clipping example. Now, last time we looked at the sprite clipping code, the code that was doing the recalculation of the sprite size, and also the basic sprite drawing code. We're looking at some of the extra tricks that I've added to it this time, because unlike the previous sprite drawing example, we're using a few extra things to improve the speed. The first thing we're using Stack Misuse to clear the screen in between redraws, and we're also using it to read the sprite data a little bit more quickly. This is where we use the stack pointer for its unintended purpose. We, instead of using it for temporary storage, we actually use it as bulk reading or writing. The other thing I'm doing is I'm using screen buffers, and so we're drawing to one screen buffer and showing the user another one, and then we are potentially swapping them over, and potentially means only on the Spectrum 128K, because the Spectrum 48K can't do that. So we've got two versions of the code for that as well. Anyway, now because of the sprite misuse, when we move around the screen normally, if I use the right keys to move around the screen, you'll see we're moving in one byte chunks, but when we get to the far edge of the left screen, you can see we're actually moving in 2 byte chunks, and that's because that sprite misuse is using a pop command to read data. A pop command reads 2 bytes, so that's why we're doing that. When we get to the right hand side of the screen, you'll notice we're basically losing one block of data there, and again that's because of the way the sprite misuse, the stack misuse, sorry, is working. We're reading in 2 bytes of data, so we're writing in 2 bytes of data, so that's why that is happening. Now, we're going to go over the code today, so let's go over to the source code. What we're not going to do is we're not going to look at the source code that was covered last time. The stuff relating to the sprite drawing and the cropping, please see episode 24. That will be for that, because I covered that last time. Okay, over we go to the code. Here it is. So, as always, you can get this from my website, and you're welcome to use it in any way you want, or you're welcome to point it and laugh and make a better one if that's what you're able to do. Good for you. But we're going to have a look at this thing today. Now, the first thing we're going to look at here is the flip buffer command. Now, the flip buffer command is only enabled if the use hardware buffer is selected. Now, we are using buffering in both cases, but the hardware buffer can only be used on the Spectrum 128 and the Plus machines. So we on the regular 48K we can't do that. The only way we can have a buffer is to use a software one, which is just a clever way of saying we copy all of the data with some kind of LDIR command. So that's our only option on the 48K. Now, in the case of this code, I've just got a compiler directive. I've got this symbol that I'm defining, and we are conditionally enabling part of the code. But in a real game, you would probably want to detect which version of the machine you are using, usually by turning on the memory and seeing if the memory turns on, because if it does, you're on a 128K machine. If it doesn't, you're on a 48K one. But I've got another tutorial on that on my platform tutorial on using extra memory. Now, when it comes to using the hardware buffer, we've got this flip buffer command here, which is doing the job. Now, we're going to use port 7FFD to actually do the job of turning on the extra memory. We're going to page in bank 7, which is the only other bank that can be used for a screen buffer. There's one in bank 5, I think it is, and that's always at memory address 4000 onwards. The alternative one is memory bank 7, and we can only page that in to the C000 and onwards range. So we're going to have that paged in, and this port 7FFD, this is used to select the bank that is at memory address C000. That's done with bits 0 to 2. So the least significant 3 bits there are going to be set all to 1, which pages in bank 7. The bit 3 there, though, that is selecting which of the buffers, either page 5 at 4000 or page 7 at C000, is the one that is actually visible. So we're going to toggle that, and we're using that XOR command there, which is going to toggle it and also enable the bottom 3 bits turning on the page that we want. Now, port 7FFD is the one we want to actually control, but there is actually a backup of that in memory at memory address 5B5C. So we're reading in that current value and we're setting it back, because if at any point we want to use the firmware needs to know the correct setting for that. And so why not keep that correct, because we need to keep track of what we've selected anyway. So we're going to use the memory address that is already used. Now, what we need to do then is we are going to take that bit that we are basically toggling here, and we are going to XOR that, and that is going to select the opposite screen. So one is going to be visible, the other is going to be drawing, and we're shifting that from bit 3 here and we're going to rotate that to the left 4 times, and we're then going to OR in 4000 here. We're only doing the top bytes, we're ORing 40, and that's because we're going to use either memory address 4000 or C000, and so we need that top bit to be a 1 or a 0, and the next to top bit to be always a 1, so that we've got 4000 or C000 as our screen base. So we're then using self-modifying code here. We're modifying that value into screen base +1 here, -1, and that is part of our code that is being used for the calculation of the memory addresses. So we're modifying that straight into our code, so we don't need any more temporary variables. And you can see I've got these calculations there. We'll see that in just a moment. Now, that's the bitmap data, the black and white data, if you will. We also have the color data, and of course we've got 2 screen buffers, so we've got 2 copies of the color data, and they start from usually 5.8 onwards, but if the base is C000, then that will be at D8 onwards, and so we're calculating that second address, and we're modifying that in as well. Now, this is all we need to do to flip the buffers. We've modified our addresses that the memory will write to next time we're drawing a screen, and this command alone is enough to change the visible screen, which is why it's so fast. So that's what we're doing there. Now, here is our self-modifying code, and you can see here that this is 1 line after this OR command here, which is ORing in the memory screen base. So that will either be C0 or 40, and so we were subtracting 1 from this address. I always put +1 or +2 or whatever modifications need to be done to the label to get the byte that I'm trying to self-modify, and so we would modify that C0 to 40 in our running code automatically. That's what the self-modifying code is doing. Now, there was a second one, and here it is. So, and this is being self-modified in for this CLS command at the start draw. So that is selecting the color area, but we're actually using it because this CLS command is using Stack Misuse, and that works backwards when it's filling. So we're starting at the end of the bitmap data, and we're filling the range. So we've got that second self-modified line there, and again we've got +1 there because we're changing the top byte of D800, and that's a little endian system, so the D8 will be the second byte in the parameter of that 3-byte command, so at the very end. So that label is 1 byte onwards, so I've put +1 so that I remember to subtract 1 when I'm doing my calculation. That's the way I give my labels when I'm doing self-modifying code, just so I always remember to do the correct subtractions and additions there. That's what I prefer to do. Okay, so that's what we're doing if we've got a hardware buffer. What if we're on the lowly 48K and we've got no hardware buffer? Well, we're going to have to just copy the memory, or have no screen buffers, but we're going to copy the memory and use a screen buffer. Now, we could use a simple LDIR command, but the LDIR command is pretty good, but it does have a bit of a limitation that all of those R's in the LDIR command, the repeat loops, that's an extra condition, and those conditions do take a little bit of processing power. Now, we could use Stack Misuse here in some way, but actually the basic LDI command, if we unwrap the loop, and I'll explain what that means in a minute, is actually as fast as Stack Misuse. And so what we've got here is a huge sequence of LDI commands, 48 of them in fact, and then finally we've got a DJNZ at the very end here. So we're doing lots of copies and very few loops, and this makes it more efficient, and that's what's known as unwrapping the loop. If we have a command like a copy command and we have a loop, if we want to do this 40,000 times, if we do that conditional loop 40,000 times, that's going to be very slow. But if we do the copy command 40,000 times with no loops, it's going to be very fast, but use probably all of our memory. And so what we've done here is basically a trade-off. We want to copy 1800 bytes here. We are doing 48 copy commands. We're using LDIs here, and we've got a loop of 128. So 48 times 128 equals hexadecimal 1800. So we're copying all of our data with lots of copy commands and only very few loops, and this is pretty damn fast. So this is, as I say, known as unwrapping the loop, and it's one of the very important tricks for optimizing 8-bit code and making it as fast as possible. Essentially, with 8-bit code, what you end up with is you have a trade-off. Basically, you can either have very fast, very big code, or very small, slower code. You're swapping memory for speed in most cases, and also, unfortunately, when you are gaining the speed, you're also usually making your own life harder, because self-modifying code, Stack Misuse, these are more prone to causing bugs. So just another thing to bear in mind there. So that's how we are doing our hardware screen buffers. Well, what about this CLS command? Well, this CLS command is using stack misuse, and we are using it to fill data. Now, the stack misuse wasn't very helpful when we were transferring bytes from one place to another, because we can only use the stack misuse to read or write. We can't use it for both at the same time, and because transferring data needs both, it doesn't necessarily produce that efficient results. So I wasn't using it there, but in this case we're looking to fill a huge area of data with just one single byte. So what we're doing here is when this command is called, let's just see it, let's see what we're looking at. So what we're passing is we're passing a fill color in the 2 bytes D and E. We have to pass 2 bytes because we're using push, which transfers 2 bytes at a time. We are setting HL to the end of the range. Now in this case we are specifying, we're actually using this here to fill the color blocks here. So we're specifying to the end of the color block range, but we are also using this command to fill the bitmap data here. So we can use it for both, because basically it's just it's called CLS, but it can really just fill blocks of data. So HL is being pointed to the end of the range, and B is being pointed to the number of bytes we want to fill, divided by 64. So if we want to fill 1800 bytes, we need to divide that by 64, and this gives us a value to put into B as 96. And then we run our CLS command. Now our CLS command, here it is. This CLS command is starting by loading IY with 0. Now we're going to misuse the stack here, which means we're going to actually use it for filling data rather than as a temporary store. This means that the stack can't be used for anything else while we're doing this, and it also means that we need to back up the real stack pointer somewhere, and in this case I'm transferring it to IY, but there's no command to directly transfer the stack pointer to IY, so we're loading IY with 0 and we're adding the stack pointer to IY as a way of doing it. So that's what we're doing there. We're then transferring our end of our range we want to fill from HL into the stack pointer. Now it should be noted that at the end of this code we are restoring the stack pointer by transferring IY straight to the stack pointer. We can do that, we can't do it the other way. It's a very weird set of commands that are available to us using the stack, but that's the way things are. Now, while we've got this incorrect stack pointer, with this stack misuse as it's called, we have to be very careful as what else happens. Now, generally speaking, as a basic rule, we can't do any calls and we can't do any temporary data pushes or pops while we are misusing the stack. That's not technically true. There are ways you can do it. I've covered it in my interrupt tutorial. I've done a tutorial on how you can write very clever interrupt handlers that do allow you to use stack misuse while interrupts are still running and things, but for a simple rule you can't. So we're disabling interrupts here before we start, and you would want to enable them at the end, but I'm not enabling them at this point. I'm leaving any executing routines to enable them if they require, but for safety I am disabling them. Now, once we've got the end of our range, we are then doing a sequence of pushes. Each one pushes 2 bytes, effectively filling the entire range with the value in DE. And this is a very, very fast way. It's the fastest way of filling a range with a solid value. And there's no better way on the Z80. This is how Chibi Akamas did its background. The background gradient was done by, for each line, doing a series of pushes, changing the byte that was being entered, doing a series of pushes, moving up the screen, doing it in blocks and using different routines of code. The later game, episode 2 and version 1.666, that had clever code that could do things where I was doing sequences of pushes using 4 registers with 4 different bytes, and that was creating a kind of a repeating bitmap. It was all done with stack misuse because that's the fastest way to clear a screen. So that's what we're doing there. So that's stack misuse being used to clear a screen or to fill large amounts of data. Very, very good, very worth bearing in mind. We are also using stack misuse for the purpose of reading bitmap data though. Now here is the version that is using stack misuse. So what we're basically doing here is we're doing the opposite. We're not using it to write data, we're using it to read data. The reason for this is we're going to need to change our screen destination after each line. And we do have the advantage when we're writing to the screen that we know we only need to increment the bottom byte during a line of the HL pair, which is a little bit more efficient than doing both. So that gives us a small advantage for the writing side. So we're going to use Stack Misuse for the reading side instead. So what we're doing here, we can't use the IY register to back up the stack. It's in use. So we're using self-modifying code. We're backing up the real stack pointer to stack restore +2 here. Where's that? Well, it's right at the end of our routine before we return. So the line after this SP0 here, but we won't actually load the stack with 0. We will load it with whatever was self-modified in by our line here. So that's the backup and the restore of the true stack pointer. We're then loading IY into the true stack pointer, and from this point again we can't use the stack for normal purposes. So we've got our commands here that are going to fill our bytes of the screen. So basically our screen destination is HL. This is actually using XOR. Not really any reason anymore because we're clearing the screen each time, but I like the XOR sprite as a simple example, so we've still got that XOR code in there. But basically we are popping 2 bytes from our source bitmap here that is now being pointed to by the stack because we transferred the bitmap source from IY to the stack pointer. We're then loading in E into the accumulator, XORing it with the screen memory and dumping it back. Now if we weren't doing XOR, we could change this A to an E here and remove that XOR line. That would be even faster, but as I say, the XOR is still in here, so we do have to go via the accumulator. Once we've done the E byte, we then do the D byte. Notice there's only 1 read and 2 writes because we're reading 2 bytes at a time. That's why this is so fast, but it's also why when we get to the edges of the screen the cropping is a little bit crude. So that's what we're doing for each line. Now the get next line command, you'll notice, is a jump because we can't really do a call. If we did a call, that would alter our source bitmap data, and again you can be very clever and you can kind of get away with things like that, but it's not easy. And if you're watching my tutorials, I would suggest you don't do it because it's a more advanced thing, and I'd suggest you start a little bit easier with Stack Misuse and get yourself a bit more confident with it before you start trying to squeeze every kind of trick out of it. But anyway, so this is the get next line routine. It's exactly the same as it was before. It just ends with a jump here, jumping back to the next line of the code here, and then it just carries on. Once the stack is finished, we can then do our return, but we can't do any calls or returns until the stack is back to a proper value. Now, if we are clipping our sprite after each line, then this get next line command will be self-modified in the same kind of way as before. And so we've got our self-modified version here. We load HL with the amount that we want to skip of our source bitmap after each line, and we're just updating the stack pointer after each line. Now, this version here you can see is capable of cropping even though it's using Stack Misuse. However, I would actually recommend you don't do that in a real game. What I would suggest you do is you have 2 versions of your code. You have your super fast Stack Misuse all the way, every trick in the book version for when the sprite is entirely on the screen with no cropping required. When you need to crop the sprite in any way, I suggest you use a simpler version which probably doesn't use any of these kind of tricks, because you can see there's limitations when you get to the edges of the screen of what you can and can't do. So, and you start to lose the efficiency of the Stack Misuse anyway. So as I say, I'd suggest you have 2 versions. Chibi Akuma's had a wide variety of sprite drawing versions. It had versions for transparency, versions for non-transparency, versions for clipping, a version for the clipping at edges, which was used for both of those. It wasn't capable of non-transparency, I think it was, and it also had versions for specific sprite widths. That was again for efficiency because you can have fewer conditions, and that, like unwrapping the loop, you can make your code faster. And so there were a wide variety of different sprite rendering versions, and that again was sacrificing memory to gain the speed, which, as I said before, is often what you have to do with retro programming. So there we go. So that's the end of what we're covering today. Now, as I said before, you can go to my website, you can download the source code, and as I've said, you can download the build scripts as well. And if you want to use parts of the code in your own games, just go ahead. You're welcome to use it in any way you can. That's what I put it there for. If you've liked what you've seen, please like and subscribe. You know the drill, because we'll be coming back to the Spectrum again in the future with more programming. I've got a tarmap tutorial coming later on. I've made some software tarmap code which I've been playing with, so hopefully you'll want to see that as well, and you can maybe combine that with the sprites and end up with like a simple game engine. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.